So good evening all. I am Pramod Gaval, research scholar, Department of Chemical Engineering. So I am a teaching assistant of this mass transfer operation to course. So I'm going to take a problem solving session for week 4 drying operations. So here is a brief recap. Classification of dyes, then drying calculation there. So it includes cross circulation drying, through circulation drying, then material balance and energy balance in the continuous dryers. So based on this topics, so I'm going to take a problems. The problems include MCQ and also numericals. So before going to start, just I have to check. No one has joined. Okay. So classification of common dryers. It classified direct heat dryers and indirect heat dryers. Then direct heat dryers classified batch and continuous. And indirect heat dryers classified in batch and continuous. So here is a different types of dryers which include in the batch and continuous modes. So based on that, so we are going to first see the MCQ questions. So question 1, which of the following is an example of direct dryers? Option givens: tray dryers, fluidized bed dryers, vacuum dryers, freeze dryers. So you can see these flow charts. So direct dryer, here is a dryer. So you can see options: batch fluidized, tray dryers comes, tray dryers 1. Here is also tray dryers. And also fluidized bed dryers, vacuum dryers, vacuum that's come in which indirects not. Here is a tray dryers in a direct dryer, tray dryers and batch fluidized bed dryers. This option A and B, but it should be the one. So it should be like a change like drum dryers. So like now option B is correct. Now question to: which type of dryer is the most suitable for the drying heat sensitive materials? So spray dryer most suitable for drying heat sensitive material. Now question 3: which of the following dryers operate under the reduced pressure to lower the boiling point of the mixtures? This is here is in the concept in this question. Thus you can directly say that vacuum dryers reduce the pressures to lower the boiling point of the moisture. Question 4: which type of dryer use indirect heat transfer for drying materials? So here you can show that flow chart. Based on that you select. So is a 1 minute. Which type of indirect uh, drum dryers, rotary dryers? Rotary dryer comes into the directs. This is not vacuum dryers. Vacuum dryers comes in a 1 minute. Is it not mentions? drum dryers, so it possible because it mentioned that the indirect heat transfer for drying materials. So drum dryers and tray dryer. Tray dryers comes in a direct heat. So here is a option B is correct. If question 5, if the initial moisture content of material is 70% on a weight basis and final moisture content is a 10% weight basis, what is the total weight of the water removed from the 100 kg of weight materials? Right, total weight of waters. Right. So here is a weight material given 100 kg. Right. So you have to first calculate initial moisture content is equal to 100 into 0.7. So here is a moisture content given on a weight basis, and so how much dry weight? Dry weight is 100 minus 70 is a 30 kg, right? Since the final moisture contains is a 10%, right, weight basis. So this means 10% of the final weight is a final weight of waters. So the final weight equal to dry weight plus final weight weight final water weight, right? So let the final weight be, let the final weight is considered the WF, right? Now final moisture contain given here 10%, contain weight basis, is equal to final water weight divided by this final weight of the material. That's the WF equal to 0.10, right? Now WF dry weight, here dry weight 30 kg plus 0.10. So final weight 0.10 into WF, right? So WF is, so you'll get the WF is equal to 33.33 kg, right? Now final weight, final water weight, final water weight equal to WF into 0.10, WF into 0.1, so it's a 3.33 kg, right? So in this questions, what is the total weight of water removed from the 100 kg of wet materials? So initial water 70 kg. So water removed. So initial water weight minus final water weight. So 70 minus 3.33 is equal to 66.67 kg. So 67 kg of water removed from the 100 kg of materials, weight materials. Options here. Moving to the question number 6. 1 minute just. It is working smoothly. Yes. The question number 6: if the drying rate is a drying rate in a constant rate period is a 5 kg per hour, how much moisture will be removed after the 4 hours during this period? Right. So moisture remove is equal to drying rate into the time durations. So moisture remove equal to drying rate. Here is a 5 plus time duration is a 4. It's a 20 kg. Right. Option C is correct. Question number 7. Consider a constant rate drying of a mice solid on a tray. The substantial heat transfer to the solid occurs from the tray floor if the weightable temperature of drying gas is TW and surface temperature of the TS. Then here are the option given. So here constant drying. So when at a constant drying rate, the TS is equal to TW. So means TS, this solid temperature equal to the weightable temperature. So when the substantial heat transfer from the tray floor, the surface temperature of solid is slightly higher than but close to the weightable temperature of drying gas. So TS is slightly greater than weightable temperatures. Option C is correct. Question: in a drying process, reduce the moisture content of materials from 40 to 15% weight basis. If initial weight of material the 200 kg, what is the final weight of the dried material? So what is the final weight of the dry materials? So here the moisture content given in a weight basis. So we have to calculate the final weight of the dry materials. Number 1. So initial weight of moisture 200 into 0.40, so 80 kg. So dry weight is a dry weight of materials 200 minus 80, so that's the 120 kg, right? Now the final weight of the moisture equal to dry weight plus the remaining moisture. So here the final the 15%. So it means 85% of the dry materials. Let WA be the final weight of material, right? So dry weight equal to WF into 0.85, because here is a moistures means waters. So of 0.15 moistures, so 0.85 version of dry materials. So 120 equal to WF into 0.85, right? So WF is equal to 141.10 kg, right? So is the final weight of the dry materials 141. So option here is correct. Moving to the question 9, a material with an initial moisture content of 50% weight basis is dried until the moisture content reach the 5%. If the initial weight of the material 300 kg, what is the weight of the dry material? See the same concept here you have to apply. So initial weight initial moisture weight 300 into 0.50, so 150. So dry weight is a dry weight of the materials, means weight of the dry materials weight is equal to 150 kg. Here is unit kg, right? So dry, now similar concepts. So here W 150 WF into is here 5%. So 5% were the moisture. So 0.9 per 95 of dry materials. 0.95. So WF is equal to 157.89 kg. Right? Options here are correct. Yeah. So in a cross circulation drying, the airflow direction is so option given parallel to the material flow, perpendicular to the material flow. You can see in this image the air flow. So here is a air flow, here is a solid. So it's a perpendicular to the material flow, right? In cross circulation drying, increase the air velocity generally result in increase the air velocity. So there is one option, the increase the drying rate, right? Question 12. The cross circulation drying is particularly useful for the material that have uniform shape and size required uniform drying across the entire surface. So generally the cross circulation drying is used for a required uniform drying across the entire surface. Question 13. In a through circulation drying, air passes across the surface of the material through the bulk of the materials around the materials, none of the above. So through the bulk of the materials. Question 14. The efficiency of through circulation drying can be improved by increasing the air temperatures, reducing the thickness of material bed, increasing the air velocity, all the above. So here is the all the above. Question number 15. Which of the following factor affect the drying efficiency in a through circulation dryings? The air velocity, material thickness, the air temperature, all the above. Means all the above. Means air velocity, if you increase the air velocity, so there is a impact on the drying efficiency, material thickness also, air temperature also. So all the factors are important for improve the drying efficiency. Question 16. In a through circulation drying, the drying time is controlled by initial moisture content, no. Humidity of drying air, no. Temperature of the drying air, the thickness of the material bed. Option B. Question 17. Which of the following is considered in the material balance for a continuous dryer? Mass of wet feed, that's also considered mass of dry product, that's also moisture content in inlet and outlet, all. So here is our option D. So all this the factor considered in a material balance for a continuous dryers. Question 18. In a continuous dryers, the energy balance equation typically includes the heat input from the drying medium heat loss to the surroundings, latent heat evaporation moisture, all the above. So all these factors include in the energy balance equation. Question 19. In the energy balance of a continuous dryer, the primary source of energy loss is usually there was no heat carried away by the exhaust air, heat used by the vaporizing the matter, no. Heat loss due to the radiation, no. So here is the B options. Right. 20. So in a continuous dryer, if the inlet moisture content is 30% weight basis and the outlet moisture content is a 10% weight basis, what is the moisture removed per kg of dry material? So here is the initial and outlet moisture content given moisture in a weight basis. So what is the moisture removed per kg of dry materials? So here is a formula given for a dry basis. Based on that we have to calculate. So first calculate the inlet moistures on a dry basis based on that formula. So first inlet equal to here is 0 inlet moisture contain 0.3% divided by 1 minus this is 0.3. So generally the moisture content on dry basis, the moisture content divided by kg of dry materials. So to calculate the kg of dry materials, so 1 minus 0.3. So you will get the dry materials. So 0.4286 kg moisture divided by kg dry solid. Similarly, outlet 0.111 unit same kg moisture kg dry solid, right? So moisture remove inlet minus outlet, right? Moisture remove equal to outlet 0.4286 minus 0.111 equal to 0.3175. Unit is the same kg moisture divided by kg dry solid, right? So option E is the correct. So moving to the question number 20, while drying of solid from 33% to 1% dry basis, it is found that the constant rate drying time is the same as the falling rate drying times. The equilibrium moisture is negligible if the falling drying rate is linear in the moisture content. What is the critical moisture content of the solid given? So here mention that in this question. So TC is equal to TF, right? So here is the XI given. Here is the XF given, right? Now here is a negligible means X star is equal to 0. So in this question you have to calculate the critical moistures. So here is a formula given. So just for TC is equal to TF. So you have to just separate it. So these terms get cancelled. Here is a equal sign, right? This will also cancel, right? Now xi minus xc equal to, so here is a 0, so this term get cancelled also, right? So we'll get like xi minus xc is equal to xc ln xc minus xf, right? Here is a xf given 0.01 and xi 0.33. So calculate, so you will get the value. So I already calculated x is equal to 0.1. Moving to the question number 22. The convective heat transfer HC or a through circulation drying of the solid is estimated to be 150 watt per meter square into Kelvin. So what would be the mass transfer coefficient Ky? For moisture transfer from the surface, for moisture transfer from the surface of particle to the bulk of the air having a humidity 0.018. So in these questions, the convective heat transfer coefficient given 150, right? What would be the, so we have to calculate the mass transfer coefficient for moisture transfer from the surface to the air with the humidity given, this one's y, right? So there is a one relation to calculate calculate the mass transfer coefficient. So Hg divided by Ky, which approximately the humidity, right? So Hg means convective heat transfer coefficient divided by mass transfer coefficient, which equal to the humidity. To calculate the humidity, there, so I already saw in the first first sessions, CH is equal to 1.005 plus 1.88 yes, here is a absolute humidity. Unit is a kilojoule divided by kg of dry air into Kelvin. So here is your humidity given, so just put, so you will get the value of CH 1.03884. The unit is a this kg, kilojoule per kg dry air into Kelvin. So using this relation, so ky is equal to 520. So unit is a kg per meter square per hour. This option is right. Moving to the question number 23. A solid is to be dried in a falling rate period from the critical moisture content Xc to 1/10 of it Xc divided by 10. The equilibrium moisture is negligible. If the falling rate is in a X, the drying time is a T1. If the drying rate varies as a X square, the drying time is T2, then T1 by T2. So here the so here is a falling rate period given with the critical moisture content X to the 1/10 of final means final moisture content is Xc divided by 10. Now equilibrium moisture is negligible, right? So Ex star equal to the 0. If the falling rate is linear, the drying time. So if the here is a two condition given. If the falling rate is linear in a X, the drying time is a T1. If the drying rate varies X square, the drying time to a T2. So that's in second case, the drying rate is varies as a X square. The drying time is a T2. So then we have to raise the ratio to T1 by T2, right? So here is a consider this ones. So T1 equal to Ws divided by ANC equal to Xc, because here is a equilibrium moisture is a negligible, so it's considered 0. Ln Xc divided by final is a Xc divided by 10, right? Xc get cancelled, so it's a 10, right? Now so it's a calculate ln 10, so 2.3025. Now in second case, so n is equal to b x square, right? So b is a constant, so our direct NC is equal to b x square, right? So b is equal to NC divided by exc square, right? Now T2 is equal to Ws by A integrate xf to xc, so dx by b xc square, right? So you can write down Ws A xc square. Here is a beta given means just here is a just like here is the equation, so based on that just mm, this terms get here, so you'll get this beta x square b divided by nc is equal to 1 by fc 10 minus 1 by fc, right? So here is a t1 by t2. So you by solving, so you'll get the answer t1 by t2 is equal to 0.256, right? Option C is correct. So moving to the question number 24, the number of gas phase heat transfer unit in a through circulation drying of the solid is 3.5. So means number of gas transfer unit given. The gas temperature decreased by the 35 degrees Celsius across the bed. Okay, means delta T given. So what is the log mean temperature of drying force? So NTG, number of gas phase heat transfer unit, H denoted by the heat. So ln TGI minus TS surface temperatures divided by initial temperature minus Ts. So this is a number of gas phase heat transfer units. So is given 3.5, right? And here ask the log mean temperatures. So log mean temperature means delta T LMTD. So LMTD means log mean temperature driving force equal to Tg1 minus Tg0. So you can say delta T also. These terms ELN Tg1 minus Ts divided by T0. So you can write down NTG. 1 minute. NTG, right? So the gas temperature decreased by 35 degrees Celsius. By NTG 3.5. So it's a 10. It's a yeah. Option is a sorry. Option E is a correct. Question number 25. Weight materials weighing up 400 kg has initial moisture content up to 70% weight basis. The material is dried until the moisture content reach 10 weight basis. Calculate the total amount of water removed during the drying process. So we have calculated now how much amount water removed during the process. So initial weight of the moistures moistures initial moisture weight WT denote for the weight. So 400 into 0.7. So 280 kg, 280 kg of moisture, right? So how much? So calculate dry weight of the dry materials. Dry material weight is equal to 400 minus 280. So it's a 120 kg, right? The final moisture is a 10%, right? The final weight consider some it's a lead final weight uh, final water weight WF, right? So final moisture given 0.10 is equal to final water weight divided by final weight. That's the WF, right? So final water weight equal to 0.10 into WF, right? Now WF final weight is equal to dry weight. This is for the final conditions, dry weight plus final water weight WT, right? So WF is equal to 120 plus WF into 0.10, right? So WF is equal to 1333 kg, right? So now final water weight here is we got the final weight of materials. So final water weight is equal to this one 0.10 into this one. So you get 13.33 kg, right? Now water remove equal to 280 initial 280 minus 13.33. It's a 266.67 kg. So yeah, in this process, so 266.67 kg of water removed during the drying process. It is working smoothly. Moving to the question number 26. In a continuous dryers, 800 kg per hour of wet feed with moisture content 50% wet basis dried to moisture content 5% wet basis, assuming no loss of material other than the moisture. Calculate the mass flow rate of the dry product. So here is the flow rate given of feed of wet feed and moisture content 50%. Now here mentioned that the assuming the no loss of the material other than the moisture. Calculate the mass flow rate of the dry. So here initial dry weight 800 into 1 minus 0.5. So this is for drying materials. It's a 400 kg. So here you mentioned that assuming no loss of material other than the moistures. So the rate of the dry means the mass flow rate will be the same. It's a 400. Now moving to the question number 27. Wet solid having 32% moisture on a dry basis is to be dried on a tray dryer to final moisture 1%. Right? Here is initial given. Here is a final given. That's a except. Here is a xi. So I can write down here directly xi. Here is a except. The solid loading is 30 kg. Dry solid meter square. So here given WS by A, right? Kg per meter square dry area. There are two critical moisture value given. Xc1 is equal to 0.183 and Xc2 is a 0.097. So means first here is a first means a first falling rate period and second falling period you have to here you have to apply. The laboratory test gives a drying rate at 4 kg meter per meter square per hour. This is NC. In the constant rate period. In the first falling rate period, the flying flux, that's the NC, is this is the NC is a linear to the moisture content. In the second falling rate, the drying flux means NC, this is the drying rate, whereas as the square of the moistures. Okay, means in first case NC is directly proportional to it. In second case, NC is a direct proportional to the x square, right? Case 1 and case 2, right? The equilibrium moisture is negligible. Calculate the drying time in hours if the drying condition are the same in the laboratory test. So here is a formula given for to calculate the TC means time in a constant rate period. So here is a TC is equal to WSA XI minus XC1 divided by NCA. And the first falling rate period, so TF is equal to the WS. So here is some derivations. So here is a formula last. WS is equal to dE into 2xc1 minus xc2 divided by twice in NC into ln NC1 divided by NC2. And for second falling period, so you'll get here is a formula WS into xc2 2xc1 minus xc2 divided by NC into 1 by xf minus 1. So all the value given, just you have to here you have to put the value, so you'll get the value. So I calculate already TC is equal to 1.027 hour and TF1 is equal to 1.029 hour and TF2 is equal to 17.552 hour, right? So total time is equal to TC plus TF1 plus TF2 equal to 19.6 hour. So moving to the question number 28. A granular wet solid is taken on a tray 1 meter into 0.6 meter and dry in a stream of the hot air 120 degrees Celsius and humidity 0.02 kg per kg of moisture per kg of the dry air. Velocity u given 4.5 meter per second. The initial moisture content is 30% on a dry basis is to be reduced to the 0.5%. Right. So from the laboratory test, it is known that the critical moisture content is 12%. So it's a Xc. And equilibrium moisture is a negligible, means X star is equal to 0. So I can write down here directly Xc. Here is a Xi. Here is a X. The falling rate of drying is linear to the moisture content if the solid loading on dry basis is a 40 kg per meter square, means W by A given 40. Calculate the drying time. Assume that the airflow is a large and its temperature drop across the tree is a small. So here are the some properties value given. TW is equal to S 41. So wet belt temperature given 41.5 degrees Celsius and humidity given 0.0545 kg per kg dry air. Temperature is 1 atm. Latinity vaporization of water at 41.5 degrees Celsius is a 2400 kilojoule per kg. And SC the relation given heat transfer coefficients. Right. G dash is a gas flow rates in unit kg per hour meter square, and SC is a watt meter square into Kelvin. So here you have to calculate the time. So first here the relation SC is equal to 0.204 G in raised to the power 0.8. So to calculate the G, velocity into rho G, density of the air, right? So here is a TG given 120. So convert into the Kelvin 393.2 Kelvin, right? Now density, to calculate the density of air based on the ideals of PV is equal to nRT, right? So ANY V equal to P by RT, right? So 1 atm given, so convert into the Newton into meter square 0.325 into 10 raised to the power 5, right? So here is the mole. So here you the unit of the density kg per meter square. So you have to multiply here the molecular weight of the air 29. So 8.314 it is a gas constants into 10 raised to the power 3 to 393.2. So 0.898 kg per meter cube, right? So put in this equation. So you given 4.5 meter per second. So you have to here convert. Let's see. 4.5 seconds. So 4.5 4.5 into 0.898 into 3 seconds. So 36 into density 0.898. So it's a 14547.6 kg meter square per hour, right? G. Now put in this equation, in this relation, so you'll get the heat transfer coefficient. So HC is a 43.63 watt meter square per Kelvin, right? Now so all the others like at wet bulb temperatures 41.5 degrees Celsius. So this value got from the stoichiometric charts from in the which is in humidifications chapters. So first calculate the constant drying rate. constant drying rate is equal to, that's a NC is equal to SC by TG minus TW, right? Here is a lambda. So TG given 120 and TW just 41.5. SC can just calculated and lambda W given. Calculate. I calculated 5.1374 kg meter square into hours. So initially get the unit in the seconds, you have to convert into the hours. Now xi given 0.30, fc given 0.12, x start equivalent 0, so xf is equal to 0.05, right? The solid so first calculate the TC equal to WS by A into N NC XI minus XC, right? WS by the given like 40, right? NC just calculated here is of 5.13 and XI 0.30 and XC 0.12, so it's a 1.40 hour, right? Now TF like WS into SC into SC like ln XC divided by XF, right? So put all the value here. So 0.8179. So total time required TC plus TF equal to 2.21 hour. So I cover all the questions based on these topics. So I conclude today's sessions, and we will meet on next Friday on next chapters. So thank you all.